So now let's look at how the typical energy of particles is changing over time. Now, two of the components of the universe today are solid particles, things like protons, hydrogen atoms, whatever, flying around in space. And these are called baryons, baryonic particles. And there are photons, light waves, also flying around through space. And at the moment, photons are much more numerous than baryons. There are 10 to the 9 photons per baryon right now, a pretty amazing ratio. Mostly in a microwave background, which, if you remember, is the glow from the glowing wall we talked about last time. Now, what are the energies of these baryons and these photons? Well, today they have different energies. But when the universe was very young, less than a few 100,000 years old, it turns out that it was so dense that the photons and baryons were constantly smashing into one another. And this situation is what we call equipartition. If there are enough constant collisions between them, they will on average have the same energy, which makes things very easy. So, back then they're smashing into one another all the time, constant collisions one way or the other, so they have the same energy. But which energy do they have? Do they have the energy of the baryons or the energy of the photons? Well, because the photons so hideously outnumber the baryons, it turns out it's the photon energy that dominates in the early universe. So how does the energy of a photon vary? If we can work that out, we can work out the energy of everything, because they want to completely dominate in the early universe, not today. So, we've got a photon. It's an electromagnetic wave, oscillating electric and magnetic fields, and it has a particular wavelength, which we normally write using the Greek letter lambda. For visible light, lambda is about 0.5 micrometers. But the vast majority of photons in our universe are from the microwave background, and they typically have a wavelength of about 1 millimeter, roughly speaking. So this is most of the photons today. Now, as we go back in time, space is going to expand or shrink. So going back in time, it shrinks. So let's say a given photon has some length L now. Remember, we talked about the scale factor. At some time in the past, its length back at some time would have been the scale factor for that time times the length now. And the same thing applies to its wavelength. So the wavelength at some time t is equal to the wavelength now times a of t. So how does that relate to the energy? Well, it turns out that quantum mechanics tells us that the energy of a photon is equal to Planck's constant times the speed of light divided by its wavelength. So the energy right now is equal to, if you plug Planck's constant at the speed of light and a wavelength of 1 millimeter into that, we get an energy of about 10 to the minus 3 electron volts. What's an electron volt? An electron volt is 1.6 by 10 to the minus 19 joules. It's a useful unit for dealing with very small energies. Joule, as you see, would be a much too big a unit for this. It's the amount of energy an electron gets if you accelerate it with a potential difference of 1 volt. So if you have two electric metal plates with a 1 volt potential difference between them, the electron will be accelerated by the electric field and will end up with this energy. So if you plug 1 millimeter wavelength in here, speed of light and Planck's constant, that's what you get. How about in the past? So the energy at some time t is going to be hc over wavelength at that particular time. But we know that's going to be equal to hc, and the lambda wavelength at a particular time is just the wavelength today times A of t, which is equal to hc over lambda naught 1 over A of t, and the hc of lambda naught is just the energy today, times 1 over the scale factor. So, we know what E naught is, and so we can therefore work out the typical energy of a photon at any given time in the past. And for the early universe, before a few 100,000 years have gone up, because the photons are smashing into the baryons so much, that'll also be the energy of the normal particles. In fact, everything will have typically the same energy. So that tells us the energy of a typical particle or wave at any point in the early universe.